So sorry about the last minute cancellation of class today. Turns out I have a spasm in my neck, so thank you for bearing with me. Anyway, to finish up section 14.2, there are a couple things that we needed to talk about. And as a reminder, we are thinking about two-way ANOVA, so we have two ways of classifying our data. In the archaeology data, that means that we are classifying based on the region in which the sherds were found and the types of sherds that we find. So there were 4 types and 5 regions. So you can think about this in a two-way classification. So with the 5 regions of sherds and the 4 types, that means there are A times B equals 20 different classifications, or 20 cross classifications. So that means that there are 20 means that we could compare directly. Or we could think about it in terms of these 3 hypotheses if we don't want to compare those 20 means directly. So if we're to compare those 20 means, we would say at least one of those means differs for our alternative, but that's not really helpful. So instead we look at the effects. So we could look at the effect for region, which is here. We could look at the effect for type, which is the second hypothesis, and then we look and see if the effect of region is the same for each level of type, which would be looking at each one of these regions individually, or we can think about if the effect of type is the same for each level of region, and so we'd be looking at all of those columns. And so we do this using a two-way ANOVA. So looking at all 20 of those means simultaneously, that overall model is the same as breaking it out into these 3 hypotheses, which is a little bit more meaningful to us. All right. So what we skipped last time and what I want to talk about today is what this two-way ANOVA table looks like. And I'd like you to take a minute just to maybe pause this if you want, to take a minute and look at this ANOVA table and see what looks familiar, if anything looks familiar to us. So I'd like to, before you do that, consider factor A and factor B. So in our example, this would be region for factor A, and B would be the type of sherd. And factor A has little a levels, and factor B has little b levels. We have to do this because we can no longer say that we have just generally G groups. So when we had one-way ANOVA, we could say G groups because we only had one grouping variable, but now we have 2 categorical predictors. So we're going to have to identify A levels for factor A and B levels for factor B. So that in mind, take a minute, look at this ANOVA table for the two-way full factorial and see if anything looks familiar. I hope that you've looked at the degrees of freedom first, and we see that if we have little a factor levels for factor A and little b levels for factor B, that means we have A times B total levels. So that would mean that we have total means to estimate. So that would be the total number of parameters that we are interested in. And so if we look at this overall model, if we remember that null hypothesis from before, that would be mu1 equals mu2 all the way up to mu A times B. So this is still in that framework of G minus 1 parameters for that whole model. So this is still the number of parameters minus 1 for our degrees of freedom. And then we look across and we still have sum of squares for model and the mean squares for model, and then of course our F is still mean squares for model over mean squares within. This is still just MSB over MSW. Sorry about that ruler showing up. So then let's look at within. Now that we can understand that G is just the total number of parameters, so that would be A times B, we can see that with our within degrees of freedom, that's the same thing. It's still n minus the total number of parameters. So that's just n minus A times B, or n minus the total number of means that we're estimating in this case, which is the number of parameters A times B. And so SSW and MSW, they're going to follow. So this MSW is still going to be SSW divided by degrees of freedom for W, just as up here, MSM is SSM divided by degrees of freedom for M. So the relationships that we saw before haven't changed. So if we got rid of all of this stuff in the middle, all that stuff about the factor A, factor B, and the interaction, we would still have between, within, and total. But we said we didn't like this between approach because it's comparing 20 means or A times B means, which isn't very interesting. So that's why we broke this model out into its effects. So we have the effect of factor A, the effect of factor B, and the effect of the interaction. So this is the model, but broken out. So now let's look and see if we see some similarities here between what we've seen before. Well, factor A, if we're just looking at factor A, which in this case is region, we see that there are little a equals 5 levels. So if we're just comparing the levels of factor A, or region, there would be 5 means to compare. And so that means that there would be A minus 1 degrees of freedom for those between region comparisons, or for those between level comparisons. So this is really a between question about the levels of factor A. So this is also a between, but between for A. Here we see B minus 1 degrees of freedom. Well, if we're thinking about B as type, we have 4 total means that we could compare for type. The mean for type 1, the mean for type 2, for 3, and type 4. And so if we're thinking about comparing just those 4 means, there would be 4 parameters to compare. And in order to compare those 4 parameters, we would lose 1 degree of freedom, and that would give us B minus 1. So this here, this main effect for type, this is between, but for factor B. So let's clean this up a little bit. So we're still asking the same kinds of questions as before, but now we've broken up all of that between group variability into between because of differences to region, and between because of differences due to type. And now we still have some variability that we might be interested in, and that is this interaction. And this is also between groups differences, but this is between groups differences not averaged over anything, but within a given level. So this is between for the interaction. And we've said that the model is the effect of A plus the effect of B plus the interaction. So whatever our model degrees of freedom are here, this AB minus 1, that should mean that our model degrees of freedom should be degrees of freedom for A plus degrees of freedom for B plus the degrees of freedom for A times B interaction. And that's where this A minus 1, B minus 1 comes from. If you were to take Stat 4220, the design class, you'd have a better idea of where mathematically this is, besides just sort of what's left over after we remove the main effects for A and B. But for now, just know that factor A, factor B, and the interaction factor, or interaction effect, those degrees of freedom have to sum to AB minus 1. The mean squares for A, the mean squares for B, and the mean squares for AB, interaction, all come from the same way. So the same rule that we had before, where mean squares equals sums of squares divided by the respective degrees of freedom, that is still true. So whether we're talking about that overall model, whether we're talking about the individual effects for factor A, B, or the interaction, or whether we're talking about within groups, if you just write MS equals sums of squares divided by degrees of freedom, you are okay. So the last thing we need to then look at is where these F tests come from. The F, well, up here I wrote for the F for the model is mean squares for the model divided by mean squares W. And that's if we want to test just those 20 means separately, so that overall model question. But we've also said that that's not a very interesting question. So if we want to test just that main effect for factor A, then we'll take the variability for factor A and divide by the mean squares W. If we want to test just for factor B, we take the mean squares for factor B and divide by mean squares W, and the same thing for the interaction. So notice whenever we're taking an F, F is going to be the mean squares for a given effect, and then we divide by the mean squares within. So this is still explained because my effect is explaining variability divided by unexplained. And whatever is within is what's left over. Right? So let's look at some relationships for these assured data. So I said that the model, this is without breaking things apart. So this is saying all 20 means are the same versus at least one of those 20 means is different, whereas if we look at those individual factors and the interaction term, we've got a little bit more to go on. And so let's compare. So this model says compare all 19 things, or all 19 means. Factor A for region says compare just the 5. So that's where we get these 4 degrees of freedom. Factor B says just compare those 4 types. So that's where we get 3 degrees of freedom. So this is 5 minus 1 for factor A. This is 4 minus 1 for factor B. And this is 5 minus 1 times 4 minus 1 for the interaction. And so we can see that this is in fact the whole model, because 12 plus 3 plus 4, so 12 plus 3 is 15 plus 4 is 19. So all of this together gets me to 19. 19 plus 40 equals 59, or we can see 19 plus 40 equals 59. So be very careful not to just add everything together, because you're going to have more than your total degrees of freedom, and that can't happen. And we see the same relationship. We see the same relationship between the sums of squares for the model and the sums of squares for the factors and interaction. So the model sums of squares, this is saying, what if we just say everything is between groups, but we don't care about y? And then for factor A, B, and the interaction, we're saying everything's between groups, but we do care about y. So these 3 sums of squares A, sums of squares B, and sums of squares for the A-B interaction, this equals the sums of squares for the model. And we can see that. So the 7,300, the 2,600, and the 11,000, that sums up to the total, the model sums of squares. So if we were to add everything in this column, 21,000, 7,300, 2,600, 11,000, 8,400, that would give us way more than the 30,000 sums of squares that we have for total. So remember, this is, model is between everything without having broken everything apart. So we can say model within total, or we can say factor A, factor B, A-B interaction within and total. So we can draw our conclusions, and I think we've done this. So we saw that the p-value for factor A, the main effect for factor A, is less than 0.0001. So we reject the null hypothesis that we first posited. So there is sufficient evidence that the mean number of sureds, the true mean number of sureds found, differs for at least one region. But we can't stop there, because in this two-way ANOVA context, we have to identify or indicate that we've averaged over the remaining factor. So we have to average over type. Remember, when we're doing a main effect, we are just looking at the average for these 5 regions. So we're saying, is the average for this row, for row 1, the same as the average for row 2, for row 3, 4, and 5? And if those 5 rows are not all the same, if there's a big enough difference for at least one of those rows, then we can say there's a difference. Then we can reject that null hypothesis. But in finding those row means, we've averaged over those columns for type. Our conclusion regarding factor B for type is similar. We reject the null hypothesis, that second null. The p-value of 0.0106 is less than alpha of 0.05, which I forgot to mention up here. Our p-value up here is also less than 0.05. So that's our justification. It's not just that we had a p-value, it's that it's less than our significance level. So here we also have sufficient sample evidence that the true mean number of sherds differs for at least one type. So that means on average we find more or less of one of those types when we average across all the regions in which we've been digging. Now we're comparing those column means. So now we're comparing the column mean for column 1, the mean for column 2, the mean for column 3, and the mean for column 4. And if those column means are all very similar, then we're not going to have a significant main effect for type. And if at least one of those column means differs, then we are going to have a significant main effect for type. But again, to get those column means, we're averaging across all 5 regions. Finally, we have a p-value of 0.0001 for the interaction effect. And that is less than alpha of 0.05. So there is sufficient evidence that the effective region is not the same for all types. So let's look finally graphically at what I mean by this. We saw last class about how to get the results, but I'll pull that up again. We will go to Analyze, Fit Model. Count is our response. To get the two-way ANOVA analyzed, we would highlight the variables we're interested in. We would then go down to Macros and select Full Factorial. And that gives us our 2 main effects, region and type, and it also gives us the region by type interaction. We then go to Run, and we see we get our analysis of variance. So this is our overall model. So we see we've got 19 degrees of freedom for comparing those 20 means. We get the F ratio and the p-value, but those aren't interesting because it just means at least one of those means is different. These are the results of our F test, or excuse me, of our effects test. So this is where the interesting stuff is. These are all the same as testing this overall model. So all together, this is our model. And so these are the effects that we just tested. So yes, we have a significant main effect for region, we have a significant main effect for type, and we have a significant interaction effect. But we want to look and see what that means. So we're going to come over here to the right-hand side and look at the effects for region, type, and the interaction. So for the red arrow menu for region, what I want to do is click on this LS means plot. And what that's going to do is it's going to literally plot the 5 row means that I get when I average across types. So this is going to plot the 5 region means. And here we go. So it automatically scrolls down and we can see the mean for region 1, mean for region 2, for region 3, region 4, and region 5. And so averaging across all 4 types, we can see that region 1 has the highest mean, region 5 has the lowest mean, and regions 2, 3, and 4 are all pretty similar. And this is about what we expected. This is what we saw when we looked at the side-by-side blocks plot all the way back at the beginning. And so this is, none too surprising. We can call this a means plot because it's a plot of the means. We can also call this an effects plot or a main effects plot because it is a plot of the main effect of region. We can also call this a profile plot because we can look at the profile of the effect. We can see by linking these means together how that effect behaves. If there were no effect, this would be a straight line. All of the means would be equal and they would just go straight across the screen. But because there is an effect, because the means are not all the same, we can see that the means change, and we see that in this profile. The profile is not a flat line. We see that there are changes from one level to the next, specifically as we get to region 5, where the mean drops quite a bit. Now, we cannot say that as region increases, the mean decreases, because this region is not a quantitative variable. But we can say that region 5 has a lower mean on average than region 1, for example. And that's why this plot is nice and helpful. So before, when we had just the results of our effects test, we could say at least one region had a different average number of sherds found when averaging over the types. And this LS means plot, this effects plot, helps us identify which one of those regions, or which regions, if there's more than one, has that different response. We can do the same thing for type. So if I want to know where the difference lies in terms of the average response for the different types, I can go to my red arrow menu for the type, select the LS means plot, and this will give me a profile plot, or an effects plot, or a means plot for type. And we can see that region 4 tends to have on average, type 4 tends to have on average more sherds found than any of the other types. So on average, we find more sherds of type 4 than any of the other 3 types of sherds. But by averaging over region, or by averaging over type, we're losing some information. So that's why the interaction is interesting. So we can get a profile plot or an interaction plot for the interaction. So when we look at region, for example, when we look at this first plot, we see that region 5 has the fewest number of sherds on average. And we look at the type plot, the effects plot for type, we see that type 4 has the highest number of sherds on average. But we might not always see the same profile for every region. So for example, this interaction plot says that for region 5, this turquoise, it goes for region 1 to region 2, we see an increase, but then a decrease from region 2 to region 3, and then it stays pretty much the same from region 3 to region 4. Well, when we average across all of the regions, region 1, region 2, region 3 are basically all the same, but region 4 is where we see a spike. That's not the same profile when we split it out and just look at region 5. Now let's look at region 1. Region 1 is this red line with circles on it. Region 1, everything's about the same, but then there's a huge spike in type 4 sherds. If we look at region 3, the blue line with the diamonds, region 3 has a drop from type 1 to type 2 sherds, and then another drop in type 4 sherds. These are not the same profiles, and that's why we have this evidence of an interaction. If we had just looked at this plot, this main effects plot for type, we would assume that we always see an increase in type 4 sherds. But we can see when we look at the interaction plot, it's a bit more nuanced than that. And that's why these plots are so helpful and so important to look at. We don't always get the same effect at every level and every type for each region. And even if they do increase, we can see that the increase or that change is not always by the same amount.